So good morning, guys. Today we're going to jump in and continue our discussion on boiling and condensing. So we did a lot of water boiling yesterday. So today we're going to look a little bit more closely at both boiling and condensation, or I can just say boiling and condensing heat transfer. I think chapter 13 calls it, what is it, convective heat transfer with phase change, but that just sounds boring. So today we're going to start off talking about boiling regimes and how it affects anticipated heat transfer in our system. So last time we were looking at, our pot of water, get some water going, and we talked about all the things that kind of happen in this system as we bring this water to a boil. The first thing that we identified is that we have natural convection or convective heating, where the heating of the fluid at the surface, this solid fluid interface, causes convective currents to kind of form in our system. Then as we continue to heat that system, I shouldn't say it like that, we have the onset of bubble formation. Let's not change the thickness. Where over time, now that we continue that heating, we have bubbles form at the bottom at that solid fluid interface. Initially, the bubbles will rise and collapse. And that's due to the heat transfer from the vapor bubbles to the bulk liquid. And so these will start to rise and collapse, rise and collapse, rise and collapse. And as that happens, the bulk fluid temperature begins to rise dramatically. Eventually, as those bubbles transfer enough heat, we start to see bubbles eventually escape to the surface. I'll say bubbles will eventually rise to the surface and enter the vapor air / vapor phase. All right. So they essentially escape the liquid. Now what happens if I keep heating the water? All right, Pratik, what do you think? Is Pratik here today? All right, Claire, what do you think? I keep heating the water.
If you keep heating the water, eventually everything's gonna, it's all gonna become a vapor eventually.
Technically, that can happen, yes. But between that, what happens when I just keep heating the water? Kind of in between that, before it all becomes vapor. What do we see happen?
The temperature is gonna stay the same because the energy is going into breaking the hydrogen bonding between the water molecules, right?
No, but good guess. What I'm really just looking for is that we get more and more bubble formation. And so we see this as a transition to a new boiling regime. And if this keeps happening, one thing we can identify is eventually, if the boiling happens to such a great extent, we can get to the point where T, the temperature of the liquid, becomes approximately the saturation temperature, right? And so we get into a saturated boiling state. And this fluid-solid interface gets so dense in bubbles that we cease to have a fluid-solid interface. And what we end up with is a continual vapor phase. Where the heat transfer is going to be happening now from the solid or heating element to the vapor, from the vapor to the liquid. And we're going to have essentially bubbles kind of break off of this vapor phase and escape. And so this phenomenon that we see corresponds to each of the boiling regimes that exist within a given boiling system. And these boiling regimes are highly dependent on our excess delta T. Or excuse me, our delta T excess. And what did we say delta T excess was from Tuesday? Parker, what was delta T excess?
I don't know. I'm looking.
Kamisha, would you like to help him out?
Do you want like the actual terms in the delta T of excess?
Yes.
So it's the delta temperature of the surface minus the saturation temp.
Yeah, that is correct. And so of these two terms in our system, which one do we expect to increase as we move through our boiling system? Or, if I kind of put it in another way, will delta TS or Tsat change? as the liquid is boiled. So Harrison, what do you think? Are any of these temperatures going to change?
I think it's possible. I'm having trouble trying to figure out which one it would be. Maybe the surface?
Okay. So yeah, you are correct in that. TS will increase while the saturation temperature won't. Thus, delta T excess increases as we move through boiling regimes. And so we can kind of start to see the existence and emergence of these boiling regimes, shown in the pictures here, where in this top right picture, we start to see bubble formation and, breaking off from the surface, entering the bulk liquid. As we move from this subcooled boiling to the picture in the top right, we start getting to saturated boiling, where now we're seeing a lot more bubble formation. There's a lot more bubbles existing within the bulk because that temperature is uniform and all the energy is going into the phase change. And then if we continue to see this boiling occur, we start to see this essentially thickness or distance from that heating element exists as primarily vapor. And we call this film boiling because there's a film of vapor between that solid heating element and the bulk fluid. And so we can quantify and graph these boiling regimes using this, what's known as a traditional or typical boiling curve, where initially we see natural convection, then natural convection as the system continues gives way to the bubble formation, or what we call nucleate boiling. Then as we continue, we see transition and film boiling. And so let's take another look back at some notes, and we'll explain each of these regimes in greater detail. So as I've stated a second ago, the first boiling regime is natural convection boiling. And in this regime, bubbles will not form, or I'll say do not occur, where we have heat transfer and the bulk fluid occurs through natural convection currents. What that means is those natural convection currents are keeping the temperature of the fluid at that fluid solid interface below the saturation temperature. And also our delta T excess is typically fairly low. And what we see is a delta T excess somewhere on the order of 2 to 6 Celsius. So that's that first boiling regime. As we continue on, we end into our nucleate boiling regime. Where in this regime, bubbles will form and initially collapse in the fluid. As the temperature of the bulk approaches the saturation temperature, bubbles will rise to the surface and enter the vapor phase. Or the bulk vapor phase. And in nucleate boiling, our delta T excess is on the order of 5 to 30 degrees C. And we kind of see this if I jump back to that figure. Where the typical path that we're seeing, right, is the heat flux is increasing. We move from natural convection to nucleate boiling. Then in the initial stage of nucleate boiling, the bubbles will collapse. As the heat flux, then the delta T excess increases, we start to see bubbles rising to that free surface, entering the bulk vapor phase, until we reach a critical or maximum heat flux. When we reach the maximum or critical heat flux, something interesting happens. And what happens is that our system goes from point C here straight to point E and moves straight into this film boiling curve, where if it can, it will continue up the curve in this fashion. Why? Because at that point, we're looking at operation at the same heat flux, because we're not changing the heat flux as we move and continue in this system. And so what we find is that this transition boiling region is skipped once we reach and exceed our critical heat flux. And the issue that happens because of this is that, we find the delta T excess at this maximum heat flux is typically around 30 degrees Celsius. As we see this transition from nucleate to film boiling, the delta T excess suddenly goes from 30 degrees Celsius way up to on the order of 1,000 degrees Celsius. And so we have a sudden massive jump in that surface temperature, because once again, the saturation temperature of the liquid isn't changing. So to kind of reiterate that and state that a maximum or critical occurs between nucleate boiling and film boiling. And the transition region is skipped. And so the reason this happens goes back to what I stated about the formation of that vapor film. So in this system, as we're getting near that critical heat flux, and we get into that film boiling regime, now we have this vapor phase. The liquid's got a lot of bubbles in it. All right, we're having some pretty good stuff. My top ramen's ready to go. And you got a little too overzealous. And so now the energy, entering the system, which was going towards the vaporization of our liquid, is now going into heating this vapor phase. And what do we know about the energies associated with heats of vaporization? Are they high or low?
They're much higher than sensible heat.
Right. So they're much higher than a typical sensible heat. And so now all of the energy, no, I think that was the thick version. I don't need that. Is now going to heating the vapor phase at the heating element. And at the same time, the heat capacities of a vapor is low, meaning all of that energy you were dumping into vaporizing the fluid is now going into heating a vapor itself. And so the temperature of that vapor is going to skyrocket. And so to maintain that heat flux, the temperature of the surface skyrockets too. Somewhere on the order of 1,000 degrees C. And so for a typical system, what type of metals are we going to be using?
Usually going to be like steel or stainless steel.
Yeah. So some sort of steels, right? Or if we're using something that has like a nickel or a copper, right? It's going to be one of those types of systems. And so this massive shift a lot of time ends up causing breakdown of the heating element. as there are some metals that can handle that high temperature, but the sudden rapid shift in those temperatures, any sort of impurities in that system are definitely going to show, right? Going from 30 degrees C now well over 1,000 degrees C, keeping in mind that's the delta T excess. And so this, issue or realm is also considered the onset of what we call burnout. As the heating elements essentially burn themselves out. Or destroy themselves. Now that's not for all heating elements. If they're made with the right metals and alloys, it can handle the sudden shift. But I would say your standard cooktop, not so much. And so what does that mean for us? That means when we're looking at a system like this and how to operate, we finally say, and we say never go. Do not go beyond this point. Which is why we call it our maximum or critical heat flux. And so what's often done when we operate is we identify the maximum heat flux and then operate at a certain percentage of it, say 70 to 80%, so that we have high heat flux and heat transfer, but we don't run the risk of moving from our nucleate boiling regime to our film boiling regime. And so, we operate really kind of here. Somewhere in this kind of like safety window. And so then that leaves, okay, if we have this weird film boiling, we don't want to go past it. How the heck do we have this transition boiling? Well, the way we get to a transitional boiling state is if we essentially achieve stable film formation without the destroying everything. What we can find is that we can maintain that film and dramatically reduce the heat flux till we get to a minimum heat flux, which lies at the border of transition and film boiling, which we call the Leidenfrost point. And this is essentially the heat flux where that film at the solid, now vapor interface starts to collapse. And so if we have it collapse, then we get into that transition region where parts of it have solid liquid interfaces and parts of it are showing the solid vapor interface. And so in some instances, I'll admit very, very rare, you could consider operating at a Leidenfrost point because you're still going to have reasonable heat transfer, but you're also in a very kind of energy efficient regime because you still have that high driving force, as governed by that delta T excess, but you're not having to put near as much heat into the system, comparing this point, the points of nucleate boiling versus the Leidenfrost point. So any questions on that? Does that kind of make sense? Comments, concerns? Further points of discussion?
I have a question.
Go for it.
So we're like heating water, right? Our example is water.
Yeah.
So whenever you heat a liquid with whatever container, whenever the vapors form, that can break your element. The heat transfer goes down instead of up. Like normally we're going up into the fluid, right? So the heat transfer goes down.
No, it would still be going from the heating element into the fluid.
Okay.
Because the temperature driving force would always be in that direction.
I just don't understand how we we heat an element up and it breaks, obviously it's getting too hot because the vapors form, the vapor film forms.
Did you have a follow-up? I just want to
wanna
make
find
sure
out
you're
what
good.
breaks the metal, like whatever metal we're using, and we're pushing this past the vaporization temperature, right, of water.
So you're asking why do we achieve burnout?
Yeah.
Okay, that's a fair question. We can answer that question. To do that requires changing our system. So now if we change our system from the fluid to say the solid that the fluid is being heated by, right? Our heating element, right? System is our heating element. Right? There's some energy, let's say if I've got a really nice gas stove that's being added onto that heating element. Right? So Q's coming in from that energy thermal source, right? And in a steady state system, that Q would go on into the fluid. Let me make sure that I'm actually on the notes. Okay, I am. Now, at nucleate boiling, Qin is equal to Q boiling, right? Which for right now is M lambda. And lambda is the enthalpy of vaporization. And it's also, HAS delta TXS. And so Tsat's not changing. The T surface is getting hot as a function of where that driving force is. And keeping in mind, going back to the system, as this boiling continues, I can clean up this, actually, hold on, pen mode. Now I get to play with this. You have to consider the heat flux. So the heat flux is increasing, right? But you'll notice it's increasing by orders of magnitude, right? So we're at, 1,000 kilowatt, 1 kilowatt per square meter, 10 kilowatts per square meter, 100 kilowatts per square meter, 1,000 kilowatts per square meter. All right, so we're increasing by to the powers of 10 in this system as we boil our system. So these are significant increases in that heat transfer being added, right? And so let's say we're getting close to that maximum heat flux, which is 10 to the 6th watts, or essentially 1,000 kilowatts per square meter. That's a lot of energy. And so as we go from nucleate boiling to transition boiling, Q goes from M lambda to MCP delta T, where CP is low, right? And by what I mean by low is, I think if, once again, continuing this lambda discussion, for water, I think it's on the order 2257 kilowatts per kilogram, if I remember correctly, around standard temperature and pressure. I can Google it. We have the technology. Yeah, 2260, I was close. All right. Now we can compare that energy to the heat capacity of water vapor. which for lack of so the CP of water vapor is somewhere on the order of 2 kilojoules per kilogram Kelvin, right? So 3 orders of magnitudes difference. And Q in isn't changing. The mass flow rate in a lot of ways isn't changing, so what has to change? The only thing that can change is the driving force. Or delta T. So if you know that energy input is staying the same, but now the energy, instead of going into vaporization, and then that should be kilojoules per kilogram. Wrong units. That means this is going to go up by 2-3 orders of magnitude. Which means that that vapor in that film phase is going to be really, really hot, which is what makes it a stable film. And at the same time, the temperature of the surface also has to go up to maintain that driving force. And so delta TS is going to skyrocket, as I said.
So we're putting energy and heat energy into this?
Yes, well, it's the energy we're putting in is heat energy. MCP delta T is a function of internal energy. So you're starting to see that now. Okay, well, that was quite the tangent, but I still think worth the discussion. All right, so any more questions on the boiling regimes? Happy to answer. All right, if not, let's shift gears and talk about calculations and our boiling heat transfer systems. All right, so in that first regime for natural convection, we don't really do a whole lot in that. So if I would say see the natural convection age calculations in the book. I believe it's in chapter 12. And the question then goes, okay, well then why aren't we talking about it if we spent some time talking about it? And the straightforward, honest answer is we're engineers and we want to operate efficiently. And you know, it's all said and done, natural convection isn't just efficient, right? That's why we do forced convection. And that's why when we're looking at systems that are boiling, we operate in our nucleate boiling regime. So our calculations are going to focus on the nucleate boiling regime. And it's called nucleate boiling regime, surprised nobody asked, is because our heat flux, little q dot, is going to be dependent on our surface's ability to generate nucleation sites. So what do we think nucleation sites are? Kiki, you're up.
I honestly have no really clue what nucleation sites are. Nucleation sites.
Take a guess.
Sites where heat transfer can occur, just like where bubbles can form.
Yep, there you go. See, you knew it. You just needed to be confident. Right? So it's where the bubbles can form. Well, we won't get into the nitty gritty of that. But the point in this is it's difficult to predict. Nucleation sites. Existence kind of thing. So what do we do when we can't develop good models to predict things in engineering? I heard somebody try to say something.
Can you repeat the question, Dr. Lopez?
Yeah, of course. I would. What do we do when we can't make a good model? Right? If we can't math it out. It's a weird question, I'll admit. The answer is we essentially just rely on empirical correlations. If I could spell empirical today. And so that means we're going to have a whole lot of like constants and things in these equations. All right. So the heat flux that we can find for nucleation or nucleate boiling is equal to the viscosity of the liquid times lambda of the liquid times gravity times the difference in the densities between the liquid and the vapor of a given fluid over the surface tension of the fluid to the 1/2 power times the heat capacity of the liquid times delta T excess divided by nucleation site C sub SF divided by lambda divided by our Prandtl number of our liquid to the n cubed. And this equation, I'm sure is somewhere in your book. But C sub SF and N are empirical values which are a function of the fluid solid involved in boiling. So they're kind of correction fudge factors. You can see them here in the lecture slides for some combinations. Example, water on a nickel heating element has a CSF of 0.006, an N on the Prandtl of 1. Benzene on a chromium heating element has a C sub SF of 0.101 times with an N exponent as 1.7. So they're just empirical values you have to identify. Everything else is just essentially a function of the liquid itself. And these essentially effectively describe that solid fluid combination and the ability that nucleation sites exist and bubbles will form at that solid liquid interface. We can also calculate the maximum heat flux as Qmax equals Cc sub r times lambda times sigma times gravity rho of the vapor squared times rho L minus rho V all to the 1/4 power. And Cc sub r is a fudge factor. That is a function of heater element geometry. Here, I'll clean that up. And once again, I provided some values for you for reference. And so depending on the system, you have to consider calculation of this dimensionless length parameter, which you calculated as the element length, gravity, relative densities over surface tension to the 1/2 power. And if we wanted, we can also calculate Q min at the lead and frost point as 0.09 times the density of the vapor, lambda times sigma g rho L minus rho V divided by rho L minus rho V squared. Oh, should be rho L plus rho V. Don't know why I wrote that wrong. Oh, and I think there's another small typo here. The value doesn't make sense. And it's also to the 1/4 power. Let me clean that up. And so one thing I do want you guys to keep in mind, sorry, I know you're trying to write stuff down, is that the fluid properties,
It's not on there, Dr. Lopez.
let me guess, I'm sharing the slides, sorry, are taken at TSAT. So when you're interested, depending on the system, you say, well, we're at what temperature? It's the saturation temperature at the given pressure of the system.
What did you say the lowercase sigma stands for again?
Lowercase sigma is the surface tension of the liquid.
Thank you.
You're okay, I'll write it in for notes purposes.
In the book, it says for coefficients for film type condensation, or is this vaporization?
This is vaporization.
Okay.
All right. One thing to keep in mind is we can also, if we were interested in solving for film boiling calculations, we can calculate Q flux of film boiling as C film, it's a constant, G times K of the vapor, or the thermal conductivity of the vapor, times the density of the vapor, times the relative density between the liquid and the vapor, times lambda plus 0.4 heat capacity of the vapor, delta T excess, divided by viscosity of the vapor times delta T excess over d, or diameter of the element, all to the 1/4 times delta T excess. And C film is a function of the geometry of the heating element, and it's 0.62 for horizontal cylinders. And 0.67 for spheres. I don't know when the heating element would be a sphere, but here we are. And so it's, once again, our favorite alphabet soup type equations. The good news is, so long as you have the equation and you can identify the fluid properties and the constants without too much trouble, you don't have to worry near as much with units. I will say in order to be safe than sorry. For boiling and condensation heat transfer, I would definitely recommend doing calculations in SI units. Say that, keeping in mind I probably end up giving you English. I'll try to make sure. I'll try to keep that to a minimum. We'll see.
What is the KV term?
That is the thermal conductivity of the vapor. And it has to do with the fact that that vapor is having to transfer the heat to the liquid between the surface heating element, or the solid heating element, and the liquid. So you have to take into account the thermal conductivity as that heat transfers through the vapor. All right, so let's see if we can work an example in the 12 minutes that we have left in class. So for this example, we have water in a tank is to be boiled at sea level by a 1 centimeter diameter nickel plated heating element. What is the maximum heat flux that can be attained while still existing in the nucleate boiling regime, and the anticipated surface temperature of the heater in this case? Okay. So in this example, we're boiling water with a nickel heating element. So we'd have to take water properties at Tsat, or just simply 100 degrees C. So if I go to the Google and I look up some of these values, I find the density of my liquid is 958 kilograms per cubic meter. The density of my vapor is approximately 0.6 kilograms per cubic meter. My enthalpy of vaporization lambda is 2,257 kilojoules per kilogram Kelvin, or I'll just keep it in joules to make calculations easier. My diameter provided was 1 centimeters, or 0.01 meters. The Prandtl number at this temperature is about 1.75. The heat capacity of my liquid, 4217 joules per kilogram Kelvin. My viscosity of my liquid is 2.8 times 10 to the minus 4 Pascal seconds. And so those are the properties I believe I need. So I asked for what? The maximum heat flux. So Qmax is going to be CCR times lambda times sigma times G rho V squared rho L minus rho V to the 1/4. Oh, and it looks like I need surface tension. So my surface tension is going to be approximately 0.0589 newtons per meter. So the only thing I'm missing is the CCR value, which if I go back to those slides for a second, CCR, assuming what kind of heating element was? Nickel plated. We have to identify what L is, it seems. Because we have essentially a horizontal cylinder. We're not sure where the L is going to fall. I would call it a small horizontal cylinder. So it's 0.12 times L to the negative 0.25. So to calculate L, it's L times G rho L minus rho V over sigma to the 1/2. So to calculate L star, I have L times G rho L minus rho V over sigma to the 1/2. L, in this case, is the characteristic dimension. As it said, for a cylinder, it's the radius, so half of the diameter. So 0.005 meters times 9.81 meters per second squared times 958 kilograms per cubic meter minus 0.6 kilograms per cubic meter divided by 0.0589 newtons per meter, all to the 1/4 power. Oh, sorry, 1/2 power. I wrote that down wrong originally. Sorry, keeps jumping around.
Should the length be 0.01 meter?
No, it's the characteristic length of the heating element. And for a small cylinder, the characteristic length, L, is the radius, or half the diameter. Good question, though.
Thanks.
All right, am I going too fast, or is this a good pace?
Dr. Lopez.
Go for it.
So should we change from the notes we took earlier that Qmax is to the 1/2 and not quarter?
Oh, it is to the it is quarter. I'm getting confused with what I'm calculating. I'm sorry. Thank you.
Yes, sir.
I forget the L's and the Q's. Thank you for straightening me out. So let's see what this value comes out to be. Doing this, I get a value of basically 2 for my dimensionless length. And from my table, now that I have L star, CC sub R should be 0.12 times 2 to the negative 0.225 power. So I get CCR is equal to the 0.12 times 2 to the negative 0.25 power. and I get a value of 0.1. So with this CCR, finally, I can calculate my maximum heat flux. So Q max is then 0.1 times lambda, which is 2257, times 10 to the third joules per kilogram Kelvin, times our sigma, which was 0.0589 newtons per meter, times gravity, 9.81 meters per second, times the density of the vapor, 0.6 kilograms per cubic meter squared, times the difference of the liquid and the vapor, or 958 minus 0.6, all to the 1/4 power. So we do this, and we should get a Q max of approximately 8.48 times 10 to the 4 watts per square meter. Oh, sorry, I was off by an order of magnitude to the 5th. So just below 1 times 10 to the 6th. All right, I think that's a good place to stop. We'll finish this up and get into condensing next Tuesday. Luckily, I don't think condensing will take near as long. And since we didn't get to everything, I might end up also pushing back your homeworks and things a little bit to maybe next Thursday. I want to make sure you guys have enough time after we go over things to complete the work. Any questions? Like I said, I know it's alphabet soup on a lot of this, but it's really just, like I said, stay organized, kind of work through it piece by piece. And I don't think you guys will have any trouble. All right, if not, take care, guys. Have a great day and have an awesome weekend.
Thanks, Dr. Lopez.
All right.